Looking at the beam, it's statically determinate, so we're going to start by finding what the external reactions are, just like we would in Chapter 5. We have an external point load of 8 kip. We have an applied moment or applied couple of 40 kip feet. We want to make sure that all of our units are consistent before we go too far forward. All of our lengths are in feet. Our one external load is in kip, and our couple is in kip feet. If there was a mixture of inches or pounds and kip or inches and feet, we would probably want to put everything in the same, we want to make everything in the same units so that when we go to the equation step, all of that will make sense together. Here, kip is our standard unit of force for this problem. Feet is our unit of length. Externally, we have the 8, we have the 40. At B, we have a roller. We're going to have a BY reaction. And at A, we have a pin. And just as in Chapter 5, we have an AX and an AY. From our first picture, and we will have more than one picture. We need internal pictures since we can't see C and D in this one. In the first picture, summing forces in the X, we just have AX, which means that that's going to be 0. If we take moments around A, we'll have a negative 8 times 8. Plus a 24 BY, plus 40 from the applied moment. The reaction at the roller, BY, is then going to be 1 kip. And forces in the y direction then, we're going to have AY minus 8 plus BY. For AY, we have 7 kip. Now we have to start looking at what are we trying to find, the internal loads at C and D. It doesn't explicitly say that we want to make a cut perpendicular to the length of the beam. That's going to be the assumption we're going to make unless we are told otherwise. So all cuts are going to be, in this case, vertical that we're going to make. First thing we have to look at, they want the internal load at C, and they tell us that C is located just to the right of the 8 kip load. And that's going to be important because it's going to influence the free body diagram we draw, whether C was to the right or C was just to the left of the 8 kip load. I think a better way to think about this is that C is at the 8 kip load. We're going to analyze just to the right of that. And that's what the C plus designation means, is we're going at point C and we're going infinitesimally to the right is what the plus is indicating. So what I'm going to draw is a figure where I'm cutting it just to the right of point C, and then I'm able to keep everything to the left or everything to the right. So I'll use this as a demonstration. I'm looking right here at making a cut. As with trusses, I usually want to take the less complicated side. The answer will be the same, but I can keep everything to the left of that cut or to the right of the cut. In this case, I'm going to keep everything to the left of the cut. Like we saw with method of sections, I'm going to copy exactly all of the external forces that are acting on the structure. Just the piece that I kept, though. AX and AY are acting on it. I found AX was 0. AY was 7 kip to the right. AX was 0. AY was 7 kip up. So I include that in my free body diagram. Right, nothing is happening over here. This is 8 feet from A to C. Also externally on this segment that I kept, since I'm cutting it just to the right of the 8 kip, I can see the 8 kip load acting on this piece. So those are the external loads acting on this. Now, because I cut it at C, I have exposed the loads that were keeping this beam held together. So what does the material that we cut away do to the material that we kept? First, an internal load, P, I'll call it P sub C, so we don't confuse it with the loads that we're going to get at point D. Again, this is my cut. This is coming out from the cut, and it's going to be perpendicular to the cut. So PC is to the right. I'm going to have a shear force on this surface. I'm going to make the assumption that it's down. Again, don't worry too much about are you assuming it's up or down. As long as your answer matches your picture, that's your main concern right now. And we have some internal bending moment, I'll call M. I'm going clockwise. Again, if you say clockwise, that's fine. Your answer will just be the opposite of mine. But as long as it matches the picture, that's our concern. I've introduced these three unknowns, but since I already know this was 7K previous, I can use this. If I now sum forces in the X in my picture C, or my picture C plus, I have P sub C, and that's all. So the internal normal force at point C is 0. If I look in the y direction at that picture, I have 7 minus 8, and as I drew it, minus V sub C. The internal shear force at this point, again, negative 1 kip. And sum of moments around C, usually that's the easiest, is to take the sum of moments around that point. And we always make the assumption, this will be more important in EMCH 213, we always make the assumption that this internal normal force comes out of the centroid of the structure that we're analyzing. It won't make a difference for this problem, but it does make a difference once we start looking at stresses. So I'm just going to draw it at the center. I don't know what the cross-section looks like, so I don't know where the centroid is, but it doesn't have an impact on this particular problem. So if I take the moments around C, I'll have that internal bending moment, MC, I assumed was positive, or I assumed counterclockwise. PC acts through C. 8 kip acts at least infinitesimally close to C plus, so I'm going to ignore its effect. Minus 7 times 8. So the internal bending moment, 56 kip feet. Those are the 3 internal loads at point C when I take that vertical cut. Point D, we don't have to worry about just to the left or just to the right because there's no point load on D and there's no point moment on D. So D is just that location. I'm going to make that cut and looking at the free body, or looking at the original diagram, it looks like just less is happening to the right of that cut. So I'm going to keep everything to the right just for simplicity. I have the pin reaction of 1 kip acting at B. I have the applied moment of 40 kip feet also acting at B. Externally, that's all that's happening in this segment. And then at D, I'm going to have some internal normal force, P sub D. That has to be to the left because that's outward from the cut surface. I'll make the assumption that the V sub D, or the internal shear force, is up on this side. And I'm going to make the assumption that MD, draw it here, is clockwise on this surface. In picture D, I have now introduced 3 different unknowns. Potentially, all 3 of these internal forces are different at D than they were at C. So I can't just assume that the internal normal force is the same. It will actually turn out the same, because when we sum forces in the X in picture D, the only thing there is negative P sub D. So it does turn out the internal normal force is 0 at both points, but it doesn't necessarily have to be. When I go the y direction, I'll have, I assumed positive, so V sub D up, plus 1 kip. The internal shear force is also negative 1 kip at point D. However, when I sum the moments at point D, this will be different. By my assumption, M sub D is clockwise, so I'll have a negative MD, plus 40 from the applied 40 kip foot moment, plus 8 times 1 from the 1 kip from the roller at B. So we do see a difference between C and D here. At D, the internal bending moment is 48 kip feet, whereas at C, it was 56.